and go from current slide. Now, I need to have a question. Did we get started in 3.4 or did we just end right at 3.4? I have a mark on the page, but I have a feeling it may have been from a previous term that I neglected to. Huh?
We just finished 3.3.
Okay, and we didn't get started on 3.4. I didn't recall doing it, but I thought, yeah, okay. There are a couple of announcements. One of them has to do with why I was running late. The first mini-term ended yesterday, okay? And I had a good class, first mini-term, except some of them are really slow about getting things in. So I have been, this morning, grading 3 research papers that should have been in much earlier. And I don't want that to happen in this class at the end of the term. Hint, hint. Okay. But that's beside, sort of is the point. But anyway, so I found out the grades are due in by Friday, which is nice they gave us that long, except I'm going to be out of town on Friday. I've got to go to an articulation meeting in Mobile, University of South Alabama. So I will not be there, and that's my next, in fact, that's my biggest group of office hours is Friday morning, 8 to 12. I'm not going to be here for that. So that left the 2 hours this morning to be my last office hours before grades are due on Friday, because I have basically no office hours the rest of today or Thursday. So that's why I was working like crazy and trying to contact students who hadn't turned in work and that kind of thing. So anyway, that's sad, sad song, but, you know, get over it. But wanted to let you know, midterm has happened already. Now, they usually ask, and I'm preaching to the choir here, I think, for us to turn in, what do they call it, midterm progress reports sometime after midterm. So it probably could be as early as Friday, but I'm guessing more like maybe by next Tuesday, because they usually give us a week to do it, to give students who have D's or F's at midterm. Now, I don't think any of you are anywhere close to being that issue, except for those who haven't turned in anything. And that's 2 people, both of whom are not here. One other might be borderline, and if I could get one other thing in before next week, that would be great. Research paper would be one fantastic, or the second test. I've only got 3 second tests in, but I've still got 2 people who haven't turned in the first test. So anyway, I need things coming in, especially for those who haven't, and those people aren't here. But please move on that if you're in the position that you need it. And even if you're not, keep the stuff coming in, especially those research papers. Don't put them off till the end of the term. That's going to be the most crowded, difficult time to get things done. Get it done sooner. Okay. Next Friday, I have a doctor's appointment, eye doctor appointment across the street here at 8:15 in the morning. So that means I will not be on the Birmingham campus next Friday either at 8 o'clock. I'll be on this campus by 8 o'clock, but I'll be over there getting my eyes examined and all the junk that goes with that. And then I'll be driving to Birmingham afterwards. So I'm guessing I'll get there around 10, maybe earlier, possibly later. It depends on how long is backed up and slow they are here. I don't know. It's been a long time since I've had an eye exam, and I'm beginning to have some issues. So anyway, just want to let you know that as well. Any questions? Anything we've covered so far? Or and by the way, if any of you are in a first mini-term class or know of anyone who is, please encourage those people, to get your student course evaluations in. Not for this course, full-term classes, only the first mini-term class. So if you know of anyone that was in it, please encourage that. All right, any questions? All right, Chapter 3 is applications of differentiation. We're now in 3.4, concavity, and the second derivative test. We'll determine, our objectives here are determine intervals on which a function is concave up or concave down, okay? We'll find any points of inflection of the graph of a function, and we'll apply the second derivative test to find relative extreme of a function. Well, wait a minute, haven't we already found we have a first derivative test to tell us that? Well, guess what? Second derivative test is even easier. If you remember, just looking at the function itself, okay, you could evaluate an extrema, relative extrema, by taking the value of the function on one side or the other side of where the first derivative is 0 or doesn't exist, and see if they're less than the value at that point, okay? But that's a little more difficult. First derivative test eliminates some of that for you. You only take the first derivative on either side, and then you know whether it's an extrema. Second derivative is even easier, okay? So, let's start with the concept of concavity. What in the world does that mean? What word do you almost see there? People at home can't see this, but cave, okay? Cave usually is an opening like this. So concavity is whether you're opening this way. Think lenses too. Concave lens, convex lens. Mirrors, concave mirrors, convex mirrors. We're not going to deal with convexivity here, only concavity, and that's curvature, basically. How is something curved? Okay? You've seen in locating intervals on which a function increases or decreasing helps to describe the graph. Yeah, we want to know whether it's going up or going down. But now we're going to see how locating the intervals on which the first derivative is increasing. Not the function, that's what the first derivative told us. It told us whether it was increasing or decreasing. What we're going to do now is look at where the first derivative is increasing or decreasing. And how could we do that? Second derivative. Take another derivative and find out then what's happening. So to determine whether a graph is curving upward or curving downward. So here's the definition of concavity. Let f be a differentiable function on an open interval I. We've had that before. The graph of f is concave up on I when f prime, the first derivative, is increasing on the interval. So think of it. I've been doing this. Think of this. Here, my first derivative is close to 0, is more than 0, greater. That's concave up. Okay? Even if it's going downward, the first derivative is very negative, less negative. The first derivative is increasing in that case as well. Okay? It's concave downward when f prime, the first derivative, is decreasing on the interval. Think of this. The first derivative is very positive here, less positive, 0, less, now slightly negative, more negative. That's obviously decreasing everywhere on that interval I just arm waved. Okay. So that's what we mean by concavity, whether it's concave up or concave down. We don't use convex. Okay. The following graphical interpretation of concavity is useful. Okay. If f is differentiable on some open interval I, let f be differentiable there. If the graph is concave upward, then the graph of f lies above all of the tangent lines. Okay? Concave up, there's a tangent line, the graph's above it. There's a tangent line, there, it's still above it. Okay? I never look at it this way, but this is a good way of looking at it. The graph of f lies above its tangent line. Whereas, if a function is differentiable on an open interval, if the graph is concave downward on I, then the graph lies below all of the tangent lines. And again, interesting, but true, okay? And what this means, this is the slope of the tangent line, this is the slope of the curve at that point. That's what the tangent line is. Anything past or before that, it was a more negative slope here, less negative here, so that puts the tangent line below it. Here, it was more positive than the tangent line right at the tangent line, more positive, so it's getting larger, increasing the slope at any point. So therefore it's above the tangent line. And similarly below here, because that's the slope at that point. It was a lesser positive slope here, so it's getting less and less, going to zero, going less. So therefore, the curve stays below the tangent line at every one of those instances. Okay. Now, to find the open intervals on which a graph of function is concave upward or downward, you need to find the intervals on which f prime is increasing or decreasing. And I think we've already talked about that. Okay, here's a graph. This one right there, okay? F of x is 1/3 x cubed minus x, okay? Now, we're talking about where f prime is increasing or decreasing, so we need to know what f prime is. So you tell me what f prime is. This function. X squared minus 1? Yeah, sounds like a winner to me. X squared minus 1. And there they got it. Okay? Now this is on the open interval from negative infinity up to 0. So we're not going to go past 0 here for now anyway. Okay? Well, no, it's concave downward there. And why is that true? Okay? Because it's bending down everywhere in that interval. Now how do we know that? Let's look at this, okay? The first derivative is okay, anywhere from negative infinity to 0. At 0, the first derivative is minus 1, okay? Backing off from there, say at 1, first derivative is 0. Backing off from there, the first derivative is positive and gets more and more and more positive as you go that way. So therefore, the first derivative is decreasing as you go through that interval from negative infinity to 0. Okay, they knew to stop there, and we'll know that soon. Okay, and here is the graph of this. Now, I'm surprised they haven't already said this. When you've got the graph to look like, if it's cupping upward, it's concave up, okay? Positive concavity, okay? If it's cupping downward, it's a negative concavity. Why in the world? Well, maybe they haven't defined that yet. Seems like in my mind, that's the first thing I learned about it, and then later we found out why, you know. So it seems like that would make more sense to say, yeah, it's sure cupping downward everywhere here, okay? Cupping upward here, but we don't know exactly where that is, but we'll find out. Okay. Similarly, the graph is concave upward on the interval from 0 to positive infinity because f prime is positive there. So let's go back to the f prime. Here it was, and at 0, it has a value of negative 1. At 1, it has a value of 0. And at 2, it has a value of 3. And at 3, it has a value of 8. So it seems to be constantly increasing from somewhere around 0 to positive infinity. It just keeps getting bigger and bigger and bigger. Okay? So that means it would be concave up in that interval. Okay? Because f prime is increasing everywhere in that interval. The next theorem shows how to use the second derivative. How is the first derivative changing? Take a second derivative and it tells you where it's increasing or decreasing, just like the first derivative tells you where the function is increasing or decreasing. Okay? To determine the intervals on which a graph of f is concave up or concave down. Test for concavity. I keep putting an extra T on. Concavity. Sorry about that. Let f be a function whose second derivative exists on some open interval I. So you have to have a second derivative, otherwise you can't test for it. Now, time out a moment here. Remember those functions where we had cusps or corners? Guess what? Second derivative is not going to exist there. I didn't see you here earlier. You just came in, didn't you? Okay. I'm losing my mind, okay? Josh is here. All right, good deal. Anyone else come in while I was looking? Still all Y chromosomes. Okay. So you have to have an interval over which the second derivative exists. And by the way, the cusps and corners and points and things like that, not going to work. First derivative didn't exist there either, but at least they were up to that. Okay. So if f double prime is greater than 0, that means the first derivative is increasing. If the first derivative is increasing, for all x's on that interval, the graph is concave up. Even if the first derivative is negative, but still getting less negative, that's concave upward. If f double prime is less than 0, meaning the first derivative is decreasing, for that means the graph of f is concave downward everywhere on that interval I. Okay. Does that make sense? Just like where the function's increasing, decreasing, depending on the first derivative, positive or negative, where the second derivative is positive, negative, that determines whether the first derivative is increasing, decreasing, and that's your concavity. Okay. To apply theorem 3.7, locate the x values. Oh, where do we begin? Where that second derivative is 0. Okay. Or where the second derivative does not exist. Just like we did for first derivatives, where there's 0 does not exist. And using those x values, we determine your test intervals. Just like we did for first derivatives. Finally, test the sign of f double prime, the second derivative, in each of the test intervals. See what it is. Okay? So let's do example 1. Let's determine the open intervals on which the graph f of x, one of my favorites, equals 6 divided by x squared plus 3. Okay. Let me get a darker pen color here. Is concave up or concave down? Where would we begin? All right, good deal. Thank you. More late papers. Okay, I don't know when I'm going to get them graded. Okay. All right. Where would we begin? Second?
I rewrite the function as 6 times x squared plus 3 to the negative 1.
Hey, someone else who doesn't like doing the quotient rule, huh? I like that too. 6 times x squared plus 3 to the minus 1. Is that what I understood you to say? I like that. You could do quotient rule. It works. It's perfectly fine. I just like this better. What would you do with that then?
On the derivative.
Ah, good deal. Find the derivative of that then. And what would that be? Now, you don't have to do it this way, but this is one way. But you do need to find the derivative whichever way you do it. What would that be? Talk me through it. Negative 6 x squared plus 3 to the negative 2 times 2x. Very good. Chain rule. Okay. Now, let's clean that up a little bit. And that would be a negative 12x times x squared plus 3 to the minus 2. Now, if I were just dealing with the first derivative, I'd go on and put that back over that thing squared. But I'm not just dealing with that. We're going to have to do what next? Find the second derivative. So let's leave it in that form. That's so much easier to use. Except that, what have we got now? Not a product rule as well. And we will have to do the chain rule on part of the product rule. But how do you do the product rule? You tell me. Negative 12x, that's the first, times derivative of the second, which is a negative 2 times x squared plus 3, second, to the negative 3 times 2x. All right. Finally, the room gets to be better looking. Okay. All right. Here's the lace.
Good morning.
Good morning. Okay, good deal. Anyone else come in since I called roll? Okay. So, there's the first times the derivative of the second. We did finish that, right? Yes. Next. Plus. X squared plus 3 to the negative 2 times second negative 12. Okay. All right. That's the second derivative. Got a little bit of cleaning up to do here too. Here I see this is a minus times a minus, so that's going to make this a plus. You got 12 times 2 times 2, that makes it a 48, I'm pretty sure. And an x squared, I'm pretty sure. And at this point, I'm going to go on and put it back in the denominator. X squared plus 3 cubed. Okay? And then the second term, I believe that winds up being a negative. Yeah. And that would just be a 12 over x squared plus 3 squared. Okay. What are you going to do next? Anybody? Yeah, I got to do a common denominator here. This one's cubed, that one's squared, so what do we got to multiply the second term by to make that the same denominator as the first? Second? Anybody? Another x squared plus 3. And that would make that. But if I multiply the denominator by that, what have I got to do too? Multiply the numerator by the same thing. Because we can't change the value. Okay, we have to have the same value. Now, let's work on getting those numerators straightened out. Here we have a 48x squared. There we're going to have a minus 12x squared. What's that going to leave us with? Anybody? 48x squared minus 12x squared. Second?
You said 48 minus
48x squared minus 12x squared. 36x squared. And then the other term is just a minus 3. That's your numerator. Your denominator is x squared plus 3 cubed. All right, there's your second derivative. In about as neat a form as we could put it. Actually, there's one thing we could do to make it a little bit better. What would that be? Factor out of 3. So let's do that as well. 3 times, and what do you have here? 12x squared minus 1 over x squared plus 3.
Should that 3 be a 36?
I'm sorry?
Should that 3 be a 36?
You're right, that's a 36. I thought this is coming out really strange. Then we factor out a 36, and that leaves us x squared minus 1. I like that much better. Thank you very much. Because you had to multiply 12 times 3 too. Sorry about that. All right, much better. Now what can we do to that? Okay. Continue doing to that expression. We have a 36, and what can you do to the rest of that numerator?
You take out the x squared.
Well, it's x squared minus 1 now, right? That's x plus 1 times x minus 1. Okay? All divided by x squared plus 3 cubed. Okay. Now, we found our second derivative of f at, doesn't look very simple, but at its simplest form. Okay? I'm going to do it all class. Okay. Well, I'll find you somewhere here. Yeah, right. Okay. Huh?
Yeah.
Okay, I thought so. Had you and then I lost you. Okay. All right. Anyone else come in since I called roll? What do? We found the second derivative in arguably its simplest form, even though the earlier one looked a little easier, but this is actually simpler. What do we do with it? Set it equal to 0. Now, how are you going to get that thing to equal 0? It's the only way a fractional form will ever equal 0.
So the numerator.
If the numerator is equal to 0, okay? And if you set the numerator equal to 0, here you have 3 factors there, right? And guess what? 36 will never be 0. So that's not going to help any. But this one would produce x equal minus 1 will make that 0, or x equal plus 1 will make it 0. So the 2 points in question, x equal 1 and x equal minus 1, or in whichever order you want to do it. Okay. That's where the second derivative is 0. Okay. Now, that tells you the places where the second derivative is either, the first derivative either changing its direction or just temporarily constant. May not be constant for very long, but just at that point, the graph of the first derivative is horizontal, and it means either it's a maximum, a minimum, or does neither. Remember, we always have that option. Okay. All right. So those tell you places where, basically, other things where it's neither concave up nor concave down. That'd be the easiest thing. Where the second derivative is 0, it's neither positive or negative, so it's neither concave up or concave down. So it may be changing. Or not. We'll have to check that. So how can we check it?
Plug it in. Second derivative.
Plug what in the second derivative?
Your 1 and negative 1.
Okay, I know what that'll give me. 0 and 0. If I plug it in the second derivative, because there's the second derivative. That's how we got it. Okay. So what might we want to plug in? Say again? A little louder. Oh, yes, let's define some intervals, okay? Okay, we got the one between minus 1 and 1. I wrote them backwards. That's an interval, but we have 2 others, don't we? Less than minus 1 or greater than positive 1. So it looks like we might need to plug in some test points. Exactly, okay? And what would you like to use? -2, x equal -2. Let's plug that in the second derivative and see what we get. Do we really want to? Okay. F double prime of -2 would be 36 times a -2 plus 1 times a -2 minus 1 over a -2 squared plus 3 cubed. Okay? And am I really interested in the value? What am I interested in? Yes, it's sign. S-I-G-N sign, whether it's positive or negative. All right. Guess what, team? That's positive. Okay? No problem there. How about this one? -2 plus 1.
Negative.
That's negative. -2 minus 1. That's negative, so the product of those two is positive, so our numerator is positive. How about this denominator? Positive. Add 3 to it, positive. Cube that, positive. Guess what? It's positive everywhere, our contention, everywhere to the left of -1. So what does that tell you about concavity? Concave up. Concave up. So we know it's determine the open intervals where there's a concave up or downward. So from minus infinity to minus 1. Concave up. All right, we need another test point.
0.
0, one of my favorites of all time. Okay, so let's do the f double prime at 0. That should be pretty easy. Is it? I'm going to write it in. I was going. Let's just do it the easy way. Here's f double prime. Put a 0 here. And again, what are we looking for? The value? No, just the sign. Okay? 36 is still positive. If you put a 0 in here, that is positive. Put a 0 in there, negative. Negative so far. Put a 0 in here, positive. So guess what? Negative everywhere from minus 1 to 1, which tells you what? Concave down from minus 1 to 1. Okay. Now we need one more test point. Yeah, f double prime at 2. All right. Can we just do it this way? 36 still positive. When you plug in a 2 here, positive. Plug in a 2 here, positive. Plug in a 2 here, positive, 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 positive. Okay, y'all are very optimistic people here. So it's also concave upward everywhere from 1 to infinity. Agreed or not? All right, good deal. Determine the open intervals on which that graph, without even drawing the graph, thank you very much, we determine where it's concave up or down. I bet you they're going to draw the graph. Let's see if they do. All right, begin by observing that f is continuous on the entire real number line. We didn't do that, did we? What would have made a discontinuity there?
Denominator equals 0.
And could that ever be? No. So yeah, it is continuous everywhere because this, no matter whether x is positive or negative, x squared is positive, add 3 to it, it's equal to y. Could be 0, but add 3 to it is guaranteed to be positive. So no place where this has a vertical asymptote, which means a discontinuity. So yep, continuous everywhere. We didn't do that, but we probably should have. Okay. Next, find the second derivative. Ha! We did that one. Okay, and look at that. He either looked in the book or or they agree with us. They wrote it this way. Okay, very nice. And the first derivative is minus 6. That to the minus 3 times 2x, which when we clean it up a little bit is minus 12x. And then they wrote it back that way. Y. Okay. Okay. And now they use the quotient rule. Duh. Okay. It works. Still works. Why? I don't know. But anyway, the quotient rule. Let's do it the quotient rule way. Okay. That would be low d high minus high d low. And the d low here is 2 times that to the first power times 2x. Okay, they got that right, over low, which means you got that to the 4th power. I love the quotient rule, don't you? Okay. Now, one thing to do right here, immediately, I think, is notice there is a single factor of x squared plus 3 there. 2 of them here, but they got 1 anyway, and 4 down here. So let's get rid of one of those. Okay, so let's make that, get rid of that one completely, make that to the 1st power, and make that to the 3rd power. Let's get things as simple as possible, okay? Now, from this point, you got a minus 12x squared minus 36, there it is, okay, plus, goodness gracious, 48x squared, and that's all you've got there. Same thing we had over this. So let's see. Yep, they got 36. Boy, did they skip some steps here, okay? They did the quotient rule, and then skip steps like crazy, making it seem really easy to do. Okay, let's see how they did this. This was a minus 12x squared minus 36 plus 48x squared, okay? And the 48x squared minus 12x squared is 36x squared minus 36. Factor out that. Okay. They did it, but they did it in skipping a few steps. And then they take this and do the same thing. Well, they didn't either. Well, they said because f double prime is 0 when x is either plus or minus 1, f is defined on the interval of the real number line. You should test on these intervals, negative infinity to negative 1 to positive 1, and 1 to negative infinity. I don't know why they changed the fonts here. I guess infinities only come in certain fonts. I don't know, but this is smaller, this is bigger, and then that's, I don't know, looks like it's in between. Beats me. That's not important. Okay, so we'll check those, and they chose negative 2, 0, and 2, just like you did. And notice all they were interested in was the sign of that second derivative. Not interested in the value at all. It was positive, concave up, negative at 0, concave down, positive from there on, concave up again. And here, believe it or not, is how this looks. Okay? Because up here, and by the way, an easy point to figure is x equals 0, the y-intercept, and that would be 6 over 3, which is 2, so they graphed that one right. The rest of them aren't probably quite as easy, but a minus 1 will get you over here, and a plus 1 will get you over there. So it's looking okay. That's minus 1 will make this 6 over 4, which is 3 halves, which is 1 1/2, which looks right, and same thing there. And this is, believe it or not, an even function, even though that variable is in the denominator, it's still only squared power, so it's even function. It looks the same thing on both sides. Okay. Now, out here, you can tell as x is going to infinity, this is going to 0. Your horizontal asymptote will be y is equal to 0. Both directions, by the way. Okay? And so you see it has to start curving upward here. Otherwise, it's going to break the thing. So it has to be curving upward away from there. So concave up does make sense here. Obviously, it's concave down here. And again, because it's approaching horizontal asymptote of y is equal to 0, has to be concave up there as well. Concave down would definitely make you cross the x-axis, and you'll never get a negative number here, no matter what x you put in there. So it has to stay above y is equal to 0. Has to always be positive. Okay. So it just happens that we know now the points at which that changes from concave up to concave down. That's where the concavity is exactly 0. Concave down to concave up. All right. Make sense? Looking at the graph, I can't tell exactly that's the point where it happens, but doing it the way we did, we know where it happens, where that second derivative was 0. Okay, the function given in that example is continuous the entire real number line. When there are x values to which the function is not continuous, those values should be used along with the points where it's the second derivative is 0 or the second derivative doesn't exist. Well, guess what? If its function's not continuous, second derivative is not going to exist there either. So that's sort of redundant, but it's still a good idea to consider those and to form the test intervals. Okay. Now, I have been turning my pages like I should. They're skipping example 2, so let's us not do that. Now, a question for you. Are y'all okay with doing these extra examples even though they're not on PowerPoint? Okay, good. I didn't want to be boring you to tears any more than I already am, so we'll continue. All right, usually they save the harder ones to skip, so I thought it was a good idea. Determine the open intervals on which the graph f of x is equal to x squared plus 1 over x squared minus 4. Okay? Is concave up, and down. I'm really lazy. Okay? Concave up or concave down. Okay. How would you begin? Second? Her take a derivative, which is always a good first answer. What's that? Yes, you got to watch out for places where the function itself is not even defined. And where's that? Positive 2 or negative 2, both of those places. So, 2 places to consider. This isn't going to be, it probably is going to happen, your first and second derivatives are probably going to give you clues here too. But for right now, we know x cannot equal 2 or minus 2. Probably should say minus 2 or 2. It doesn't really matter. Just note that. Now, not a bad idea to take your derivative. All right, how you want to do this one? Yeah, I'm afraid the quotient rule will be probably just about as easy. You still could do the product rule, but I think maybe quotient rule. How does that go, by the way? Help me?
2x.
Second? How does quotient rule go here? Low, which is x squared minus 4. D high, which is what? 2x. Minus high, which is x squared plus 1. D low, which is, again, 2x. All over x squared minus 4 squared. Okay. Now let's see if we can clean that up at least a little bit. Okay? What you notice you can combine in the first term. 2x cubed minus 8x, right? Minus 2x cubed, that's looking nice, minus 2x. Okay, all over, let's leave that alone, x squared minus 4 squared. Okay, now, your 2x cubed and minus 2x cubed add to 0, and that leaves us with a minus 10x over x squared minus 4 squared. And now I'm real tempted, Dawson, to do what? Yeah, to do that, okay? Because I like doing product rule better than quotient rule, okay? The first one, that was so complicated, but boy, when that simplified a little bit, I think I'd go with this. So now we do what? And by the way, if you hadn't noticed it already, x equal plus or minus 2, first derivative is not defined there either. It couldn't be because it was discontinuous. The function was, so will the first derivative, okay? So, what's your second derivative now? Why is it what? Oh, I'm sorry. Wait, why is it not what? Oh, you're right. It is. It's there. You just can't see it. No, I'm just kidding. Okay. I'm sorry. It is a negative view. You're absolutely right. Okay? Thanks for catching it. Next. That's the disadvantage of doing this. If you don't get your signs right, you get wrong answers. Okay. How would you do this then? And how do you do that? Okay, first, which is negative 10x times negative 2 times x squared minus 4 to the minus 3 times 2x. I may be regretting that I did it this way, but let's see what's next. Plus what? X squared minus 4 to the minus 2 times the negative 10. That part was a lot easier, wasn't it? Okay. Now let's see if we can straighten this up a little bit. Here we have a minus 10x, a minus 2, and a 2x. So that looks like to me that's going to be a positive 40x in the numerator divided by x squared minus 4 cubed in the denominator. Agreed or not? Help me out here. That's a squared. I think I said squared but didn't write it, did I? 40x squared. 2x, 10x. Okay. If I didn't say it, I should have. Next, be a minus 10 is all you got left in that numerator over x squared minus 4 squared down here. What do you need to do next? And what would that be? Cubed. So we need one more down here, x squared minus 4 here. But in order to do that, we have to have an x squared minus 4 multiplied up here too. All right. Now, here's a 40x squared minus 10x squared. That looks to me to be a 30x squared. Everybody see what I'm doing there? And now we'll make it a plus 40, right? This time I'll remember to multiply. Divided by x squared minus 4 cubed. Okay. There's that second derivative. All right. The only way I can see to simplify this, unless someone can find I made a mistake somewhere that ought to be able to make it simpler, is factor out a 10, and that would be a 3x squared plus 4 divided by x squared minus 4 cubed. Okay. And what question do we ask ourselves here? Selves? No. Really all that interested in what that is? We are at one place. We want to know where that is. Well, before that, 0, right? And guess what? That thing's never 0, is it? 10's not 0. 3x squared plus 4 can never be 0, because x squared, no matter what x is, when you square it, it's non-negative anyway. Multiply that by 3, it's still non-negative. And add 4 to it, it's definitely positive. So there's no place that's going to be 0, is there? Okay. Still have those two places that we're concerned with, plus 2 and minus 2, where it's not even defined. Neither was the first derivative, neither was the function. So those are only delimiting places now, so that tells us where our test points need to be. And what would you choose for test points then? Okay, we'll choose first the -3. So we're interested in f double prime, so f double prime at -3. Okay, can we do some arm waving and deal with this? Okay, when we have a -3, plug it in here, that becomes positive 9. Okay, this is positive, that's positive, that's positive. But down here, what do we have? Okay, that would be a positive 9. Minus 4 is positive 5 cubed. Positive there. So this is positive. Okay. What's the next one you might want to consider? One of my favorites. At 0, yes. Okay. And what will that be? When x equals 0, what have we got up here? Positive 40. And when x equals 0 here, what do we have? Negative. Because you cube a negative, it's going to be negative 2. So at f prime, double prime 0, you're a negative. Okay? And what's our next one? At 2, oh, at 3. We know what it is at 2. Something beyond 2, 3 would do. And what can you tell me about that? Positive, positive. So this would be positive here too. I'm just going to do up. That's easier than writing additive. Okay. So, what can you tell me about what did they ask? Determine the open intervals on which this is concave up or concave down. Help me out. Negative infinity to negative 2, it's concave up. Okay. Negative 2 to 2, it's concave down. I'm just going to do that. And from 2 to positive infinity, it's up again. Got it. Make sense? See how the book did? Up, down, up. Good for them. Okay. Now I've been using interval notation. They've been using, the directed inequality notation, which I really like better, but this is a little easier to write, so being lazy, I'm doing it. All right, good deal. Any questions on that? Y'all seem to be catching this pretty quickly, at least the ones who are doing the talking. Are the rest of you okay with it too? Okay, good deal. If you have any questions, please ask. Let's not get too deep. Okay, so let's move on past this, and that, and that. Now to points of inflection. Okay. What we were calling before critical points with the first derivative was either 0 or undefined. Now we'll be considering, well, no, that's not quite true. Getting off into something else. If the tangent line to the graph exists at such a point where the concavity changes, then that point is a point of inflection. Okay? Now let's read that one again. If the tangent line to the graph exists at such a point where the concavity changes, then that point is a point of inflection. So remember when we had that last one, not the last one, the one before that, the one that was on the board here, you had concave up for a while. Here was the place where the second derivative was 0, and it was concave down after that. That's a point of inflection. Okay? Now, remember back here where we had a first derivative equal to 0, but the first derivative was positive on the right and positive left and positive on the right. So that wasn't an extreme value. But it is a place where your concavity changes. Okay? And that would be a point of inflection. Okay. Now, here's another one. Concave up, concave down. But here, the first derivative, okay, if the tangent line exists, the tangent line does exist there, its slope doesn't exist because its slope is infinite, either positive or negative. I've never figured out which way it's running. Then but the tangent line does exist there. It just happens to be a vertical tangent line. That's also a point of inflection. Now that last example we did, that we didn't draw a graph, ooh, that's ugly. Okay, so let me just find some space here. Remember this one? Okay. The function wasn't defined at x equal minus 2 or plus 2. So guess what? No tangent line at those points, are there? Not, even though the concavity is changing here, concave up here, concave down there, that's not a point of inflection because the tangent line doesn't exist at a discontinuity. Okay? Does that make sense? So they're showing here the ones where they do exist, where the tangent line does exist, but you can't say anywhere the concavity changes, it's a point of inflection. It's wherever the tangent line exists and the concavity changes. Whether it's a slanted tangent line, a horizontal tangent line, or a vertical tangent line, as long as it has a tangent line. But if it's a discontinuity, no. Even though you may have concavity changing, that's not an inflection point. So, here's the definition for an inflection point, a point of inflection. The FB function is continuous on an open interval. Hey, we just got rid of that last problem, didn't we? That first one directly prior to this was not continuous on it. Well, it was on 3 open intervals, but not the entire open interval. Okay? So let F be continuous on an open interval, and let C be a point on the interval. All right, good. So a point in the interval. If the graph of F, it has a tangent line at the point C, F of C, then this is a point of inflection of the graph when the concavity at F changes from upward to downward or downward to upward at that point. I think I would have worded it slightly differently, but that's how they're wording it here. So you have to have a tangent line at the point, and the concavity has to change at that point. Okay? To locate possible points of inflection, you can determine the value of x for which F double prime is either 0 or does not exist. Does that sound familiar? Yeah, we've had that before. That is similar to procedure for locating relative extrema of F using first derivatives. So the points of inflection. If C, F of C is a point of inflection on the graph of F, so you see, the way I've been approaching this is I found the places where you have potential points of inflection and then determining whether it is or not. They're saying if it's a point of inflection, which they've already defined, and then either F double prime of C is 0 or F double prime doesn't exist. To me, it's better to start with this and then go to town on finding out whether it's a point of inflection or not. But they work both ways. Okay. Any questions? So here's example 3, and that is the next one. How are we doing on time? Fine. We go to the 40. Okay. All right. I want to make sure they have the same problem. In my pre-calculus book, every now and then they'll have a problem in the book that's not the same as the slide set, even though they came from the same place. So this is the same. Determine the points of inflection and discuss the concavity, okay, of the graph of f of x equal x fourth minus 4x cubed. What you got to do first? Take a derivative. Always a good first answer. May not always be right, but it's always a good try. Okay, and what is your first derivative? 4x cubed minus 12x squared. Okay. Now, if we were interested in extreme points, we'd do something with that. We're not. They're only asking for points of inflection and concavity. So we don't really care much about it, except it's just a step to get us there. So what do we do next? Take a second derivative. Switches, take another derivative. only this time you take the derivative of the first derivative, which is the second. What does that give you? 12x squared minus 24x. Okay. Now, why would we want the second derivative? What would that tell us? Okay. The second derivative, yeah, it will ultimately tell us that, but first we want to know the potential points of inflection, and where will they exist? Where either this is second derivative is 0 or doesn't exist. Hey, this is nice, good old polynomial function. The function exists everywhere, the first derivative exists everywhere, the second derivative exists everywhere. So we don't have any of those to worry with, so we only are interested in those where this is equal to 0. Now, where will that be? And how will we determine it? Okay, say again. Factor, and what will you factor? A 12x, and what do you have left? 2. And we're interested in where those are equal to 0. And where would those be equal to 0? At x equals 0 and at x equal 2. Okay, we know the second derivative is 0 there, but that doesn't mean that we have a point of inflection there, does it? What would the second requirement be? Where the concavity changes. So we need to know the concavity to the left of 0, between 0 and 2, and to the right of 2. So give me a few points to test. Okay, so let's do f double prime of -1. And we're really not interested in the value as much as we're interested in the sign. Okay, so f double prime at -1. What is the, we do need to know the values here, I think. Okay, what, no we don't. Okay, what would the sign of 12x squared be then? Positive. And there we have a minus, but then we're multiplying it by a minus, so that would be positive, so the second derivative is definitely positive. Okay, which means it's concave up. Okay, give me another test point. F double prime at 0. I think I can do that one. No, at 1. I thought, why are we doing 0? Oh, at 1. Okay. Watch this. Okay. See, it was a 1 all along. Okay. Now, F at 1. This we do need to do a little bit of, not really much. What's the first one? 12 minus 24. That's definitely negative. Okay, so this is concave down in that interval. Okay, next. F double prime, and you said at 3. Why not? Okay. And what will the first be? 4 times, yeah, but we need to know how positive. 4 times 27, right? Goodness gracious, this early in the morning?
108.
108. Okay, positive 108. Okay, minus 12 times 9. All right, and what? Ooh, that can't be true. No. 24 times. Okay, I can't read. 24 times 9. And what's that? Oh, that's just a 3. Goodness gracious. Let's start that whole process over again. I was looking at the wrong line up above. That one right there. Okay. You know, I probably should have just looked at that. That would have been a lot easier, wouldn't it? Yeah. Why are y'all leading me astray here? Okay. Let's look at 3. 3 times 12, that's positive. 3 times that, that's positive. This is positive. Who cares about the number? So that's concave up there. Yeah, we factored it. Why not use that? Okay. At -1, this is negative. That's negative. Negative, negative, positive. That would have been easier to do. At +1, positive, negative. That would be negative. That's downward. And at 3, positive, positive, positive. Yeah. Who needed the numbers anyway? Okay, we had it factored. I wasn't even paying attention to it. All right, so determine the points of inflection. Do we have any?
0.
Yes, both of those are points of inflection because the concavity changed there and changed there. Okay, so the points of inflection.
What?
Plug into the original.
Yes, you have to plug into original function because a point is an ordered pair. And all we have is the x values here, wherever they were, 0 and 2, we need to plug in up here.
Okay, so you said the point of inflection, I mean, you about to plug those in. You said because they changed direction.
Well, the concavity changed direction.
Okay.
Okay.
In between those points. In between
Yeah, well,
values.
here were our 2 potential points of inflection, x equals 0 and x equal 2. Okay? We looked to the left, the concavity was positive. We looked to the right, it was concave up. Looked in between, concave down. Looked to the right, concave up again. So both of these are points of inflection. Except these are just x values of a point. They're not points. Okay? We need to plug in, to get the point, we need to plug in these values to the original function. So f of 0 is, that one's hard, huh? 0. So that first point of inflection is 0, 0. Okay? And it is a point of inflection. The next one will take a little more effort. F of 2 will be 2 to the 4th minus 4 times 2 cubed. 2 to the 4th is 16 minus 4 times
32.
is what? 72, you said? 32. I thought that was 72 is right. So this is that. So this is a negative 16. So the second point is 2, negative 16. Now, we found the points of inflection, done. Discuss the concavity to the left of 0, 0, or in other words, from minus infinity to 0, concave up, from 0 to 2, concave down, and from 2 to infinity, concave up again. I hope that's all we have to discuss, okay? And I hope we don't have to graph it because these numbers get really big really quickly. You're going to have to do some scaling or else you got really close points. Want to see how they did it? All right. Differentiating twice produces the following. Okay. Well, that's what you started with. Now start differentiating. First derivative, 4x cubed minus 12x squared, just like you did. Second derivative, 12x squared minus 24x, which is the same as 24x times x minus 2. Set that equal to 0, and you got points of possible points of inflection at x equals 0 and x equal 2. You don't know their points of inflection until you do the test. Okay? By testing the intervals determined by those x intervals, you can conclude they both do yield points of inflection. You skipped that step, didn't you, Book? Okay. And here's a summary of what they did, which is exactly what we were doing from 0 to negative infinity to 0. It was concave upward. We found the second derivative was positive there. Between 0 and 2, we checked it at 1, and we found that it was concave down there. Between 2 and infinity, we checked it at 3, and we found it was concave up there. Okay. But this is why I said all they're looking for was this. If we would have stopped and taken advantage of everything we had, we'd have known we also had a first derivative equal to 0 here. And then we had the first derivative equal to 0 here. We didn't stop and check this, but we would have found that. And we only found two first derivatives equal 0, and the point of inflection concave up here, down here, but then up here. It's real hard to tell. That's where it changes, but the second derivative tells you exactly where it changes. This one's pretty easy to tell. So the point of inflection can occur at a critical value as well, and but that's not an extrema. It is a critical value, but it's not a critical point, but it's not an extrema, the first one. This only has one extreme, but two points of inflection, which is not that common, but it's a little more unusual. You usually have more first derivatives equal zeros than you have second. You have two on both of these, but you have more extrema. Not always, but you can have more extrema than points of inflection. All right. The converse of theorem 3.8 is generally not true. Now, since I know what 3.8 is, but I don't remember how it's worded. There it is. This says if this is the point of inflection, then either the first derivative, second derivative is 0 or does not exist. We've already said this. Just the fact that the second derivative is 0 or does not exist does not also imply that's the point of inflection, because it could be you had no change of concavity even though you had a 0 there. Just like the first derivative being 0 here does not produce a max or min. That's not required. It is required that it be 0 or it doesn't exist, but it doesn't guarantee that you have an extrema there. Neither does just the fact that you have second derivative equals 0 or doesn't exist. Does that guarantee you have a point of inflection? I have a feeling they must be going to give us an example that shows that. For instance, this graph, f of x equal x to the fourth, shown here. The first derivative is 4x cubed, okay? And that's 0 at x equals 0. And that's the only place it is. Second derivative is 12x squared. That also has a 0 at 0, 0, okay? But that doesn't mean you have a point of inflection, because if you do a sample on one side or the other, you see it's concave up on both sides, so therefore you did not have a change of concavity. You just had a second derivative equals 0, okay? Concave up on both sides. You can tell by looking at that one. You can plug it in as well. Make sense? Okay. Now, that was example 3. Now we move to second derivative test. Oh boy, having a lot of tests in this chapter, aren't we? Okay. In addition to testing for concavity, the second derivative can be used to perform a simple test for relative maximum and minimum. We already had two. Here's one that's even simpler. This test is based on the fact that the graph of a function is concave upward on an open interval containing c, and f prime of c equals 0 at that same c. If it's concave up and it has a first derivative of 0 there, guess what? That's a minimum. Okay? No way around it. Okay? If it's concave down at a place the first derivative is 0, has to be a relative maximum. Okay? I think that's on the next page. Similarly, if the graph of a function is concave downward on an open interval containing c, and the first derivative is 0 at that c, then alpha c must be a relative maximum. Okay? So the first derivative is 0, and you know it's concave up, that's got to be a relative minimum. and if the first derivative is 0 here, and you know it's concave down, you know it's got a real relative maximum. Okay. So, it's where the concavity changes at that first derivative, then that would be here, and the only way that could change is to go like that. That would not be a maximum or minimum, because the second derivative would be 0 there. But that doesn't guarantee it's neither. It just means you have to check a little further. Okay. So here's the second derivative test. There are 3.9. So here's the given. F is a function such that f prime at some number c is equal to 0. Why c? They call it the critical value or critical point. Okay? And the second derivative, f, exists on an open interval that contains c. So the second derivative has to exist there. The first derivative is 0, the second derivative exists. Okay? Now guess what? That situation where you have a vertical thing, nope, that one, the first derivative wouldn't be 0. So that's out of the picture anyway. Okay. So, second derivative does exist on the open interval containing that point c. If f double prime at c is positive, okay, that means it's concave up, but you know the first derivative is 0 there, that means it has to be a relative minimum. F double prime is negative, but you know if the first derivative is 0 there, meaning a horizontal tangent line, then that has to be a relative maximum. So no more checking intervals for your first derivative test that we did before. We can just look at the second derivative, see what sign it is. If f double prime of c is 0 at the same place the first derivative is 0, the test fails. You failed the timing. The test fails. You have to investigate further. You have to go back and do your interval set. That is, f may have a relative maximum, a relative minimum, or neither. So in such cases, you go back and do the first derivative test. Or evaluate values in the test interval for your second derivative. Either one. Okay. So let's do example 4. Okay. And by the way, there was a proof there of that theorem. I sort of glossed right up past it. Sorry. Not really. Okay. This example, you can see larsoncalculus.com for an interactive version of this type of example. All right. Why did I write the line there? This one. Duh. Okay. Find the relative extrema. Seems like we're going backwards here, doesn't it? Guess what we're going to do first? Take a derivative. And that will be what? Negative 15 x to the 4th plus 15 x squared. All right. Figured they might give you one like this. All right. You can either proceed with derivatives, because you know you're going to have to do that, or you can do some analysis of this one. Let's go on and analyze here. What would you do next about this first derivative? I'm sorry? Okay, let's factor it and be a minus 15 x squared. Pull that out, and what do you have left? Did it go off? It'll come back. What do you have left? X squared minus what? 1. Perfect. You through factoring? Nope. That'll be minus 15x squared times. It's pretty easy. X plus 1 times x minus 1. Now, for right now, we're interested in where those first derivatives are, where that first derivative is 0. Okay? And where would be your candidates anyway? Where f prime is equal, I can't write. Okay. Okay, f prime is equal to 0. Yeah, it didn't come.
0.
Okay. at x equals 0, x equal 1, and x equal negative 1. 3 critical values here. Any place where that first derivative doesn't exist. No, it exists everywhere. Good old polynomial function. Okay? So those are our candidates for our first derivative. Well, they are where the first derivative is 0. These are critical values, candidates for either for our local extrema. Okay, relative extrema. No guarantee they're there, but if they're there, they're going to be at one or more of those 3 places. So what do we do next? Second? Take another derivative, okay? F double prime of x. Now, am I wanting to do that factored form? No. Okay? Let's take that first form. Well, it's easier to do a derivative. What does that give you? Negative 60 is x cubed plus 30x. Okay? Now, all it's asking for are relative extrema. There's no reason to find inflection points. There's no reason to find the zeros of your possible inflection points or anything like that. So all we're interested in is the sign of this thing, okay, at those 3 values. So let's check them. F double prime of 0 is 0. What does that tell us? Absolutely nothing. Okay, doesn't tell us anything. If it's 0, your test doesn't tell you anything. So, problem there. But we'll come back to it. How about F double prime at 1? And again, all we're interested in is the sign of this F double prime. So let's go back and factor this thing. Let's factor out a minus 30x. And what does that leave you with? 2x. What's that? 2x what?
Squared. So 2x squared.
2x, oh, okay, I'm sorry, 2x squared, okay. Minus 1. Okay, that's what I was looking for. 2x squared minus 1. Okay? That's going to be easier to plug in. Because all we're interested in is the sign, right? So, when you plug in a 1 here, this first one is positive. No, negative. And the second one is positive. So the product will be negative. Okay, so this will be concave down at x equal 1, so we know we have a, what kind of extrema? A max, okay, because it's concave down. So this will be a max. We haven't found the point yet. We still got to go back and do that. Let's do F double prime at minus 1. Using the factored form there, the first factor will be positive. The second factor will be positive also. So that means it's concave up. So this is going to be a min. Okay. Now, we still have to do something with that 0. Okay? Now, you could do one of 2 things and say, go back and do the first derivative test. That would be okay. I think it'd be just as good to use the second derivative since we got it here anyway. And do, well, let's see, we've just done it, haven't we? We found out that the second derivative is down to the left of 0 and up to the right of 0. Is that an extreme value? Oh, see? I'm sorry, I said it wrong. Up to the right of 0 and left of 0 and down to the right of 0. So that's a point of inflection, but not a max or a min. So see, we've already figured that, because this happens to be on either side. And that tells us that x equals 0 is neither a max or a min. It's a change of inflection there. Change of inflection without being a max or a min. Okay. So, we still haven't found the extremists, have we? What do we need to do to find the points? Plug them in here. So f of 0 we know is 0, and that's a neither. It's not a max or a min, okay? F of minus 1 is what? Is what? Yeah, negative 2. Okay, because this would be, let's work it out, just in case others are wondering where you got that. This would be a negative 3 times a negative 1 to the 5th plus a 5 times a negative 1 cubed. And this would be a positive 3, because negative 1 to the 5th is negative. And this would be a minus 2, because negative 1 cubed is negative 1. So this will be a minus 2. Okay? So this point is negative 1, negative 2. Okay? F of 1, on the other hand, is minus 3. Well, what is that? Minus 3 times 1 to the 5th plus 5 times 1 to the 3rd. And that would be pretty easy. Positive 2. So this point would be, I got them backwards here. This one is that one. This one is 1, 2. Okay. Hey, folks, we could have done that without even calculating the n. Why? What kind of function is f? It is a polynomial, you're absolutely right. It's more specifically odd. So once you knew f of negative 1, you knew f of positive 1 is going to be exactly the opposite of that, okay? Because it's an odd function. So, even more evidence that f of 0, f double prime, well, that is a neither, it's not an extreme value. Because if you look at this, you have f is concave up here, inflection to being concave down here. So there's 0 is a neither, I think. So let's clear this out of the way and see what we do. I hope I'm not said it wrong. Yeah. All right. First derivative, got it. We've got our critical numbers, negative 1, 0, and 1. Okay? They could be the extreme values or not. Okay? Second derivative, apply the second derivative test, and you've got relative minimum at negative 1, and they went on and plugged in their values, negative 1, negative 2, relative maximum at 1, 2. Okay? And then our second derivative test fails at 0. But what you could do is look to the right of 0, and you see your concave up. They didn't show that, but that's how you know it's relative minimum. And to the right of 0, you're concave down, okay, because it's a relative maximum. So you went from concave up to, say it backwards, concave up to concave down. And so therefore the concavity changes at 0, 0. So you have neither a max nor a min. because the second derivative test fails there, you can use the first derivative test to observe that f is increasing to the left, decreasing to the right. Yes, you could have done that as well. Okay. But since you already knew I was wrong on that. You did have another point of inflection here. So I kept thinking it's got to be concave. Yeah. So second derivative doesn't tell you definitively. It told you were concave up here, but it didn't tell you were concave up here. Obviously you're not. You're concave down. Since we didn't do, if we had done the full second derivative test, then we would have seen that we did have a point of inflection there, so you're concave down there and concave up there, and then that would have worked. You couldn't do it just based on what we said, so I was wrong on that. It kept not making sense to me, but I thought, yeah, because we didn't check to see that other point, the other 2 points of inflection. Obviously, you have a point of inflection here because concavity changes, but it didn't change from up to down. It changed from down to up because there was another 2 points of inflection there we didn't even look into. Sorry. So first derivative test would have been the safer thing here. You already had the first derivative. It was back here. I think I erased it, didn't I? Yeah, sorry. But real easy to plug in there. But the trouble is you have to get, anywhere between the zeros would have worked. Between -1 and 0 would have worked. They didn't show that either, but their graph shows it. All right. Whoa! Last slide. And it is the last example even. So we did finish 3.4. And right on the nickel dime too, because we're just about out of time. Homework exercises here. Please do number 3. It's at calcchat.com. Then do any of the odds 5 through 15. They're all at CalcChat. 13 is at CalcView. Any of the odds 17 to 31. They're all at CalcChat. 17 is at CalcView. All of the odds 33, or any of the odds 33 to 43. They're all at CalcChat. 37 is at CalcView. Either 47 or 45 or 47. They're both at CalcChat. 49 is an exploring thing. The concepts, if you want to go for it, it should be at CalcChat. 51 is at CalcChat. Either 53 or 55 or both. They're both at CalcChat. 53 is at CalcView. You can think about doing 57 if you'd like. It should be at CalcChat as well. 59 is a conjecture. You can try that if you want to at CalcChat. 61 you should be able to do at CalcChat, and it's also at CalcChat. 63 should be able to be done as well, and it's at CalcChat. 65, 67, you can do either one of those. They should both be at CalcChat. Any of the either 69 or 72, they should both be at CalcChat. 73 is one they say you need a graphing utility. You can try it. Otherwise, I have a feeling that one almost will require that. 75 is or 77. Both are true false. You can look at those. And then if you're really into doing proofs, try number 79. All right. Now, limits at infinity. I'm pretty sure I'm not going to test you on this part. And I'm wondering if we ought to at least do a slideshow on it. Perhaps I'll do that, just a slideshow. And also there's, as I was paging through, Maria Gaetana Agnesi is a fairly famous mathematician just because she's, as they say here, one of a handful of women receiving credit for significant contributions to math before the 20th century. It's a shame. It was almost a crime. But she was so bright. I think her dad was a mathematician or something. And just a little phrase here. By age 30, she was an honorary member of the faculty at the University of Bologna. Why honorary? They couldn't be members of the faculty. She was bright enough, sharp enough, they wanted her to be, but by law she could not be. What a shame. Okay, so anyway, potential paper topic if you're interested. We'll just do, hopefully that fairly quickly, slideshow on this, and then we'll go into summary of curve sketching, which is going to tie everything we just did. That's why I sort of didn't want to have a huge break there. What we just did with first and second derivative tests, we'll put it all together there. So we'll do a quick slideshow of 3.5, and then we'll actually do 3.6. Okay. Probably skip 3.7 as well, even though it's a great section. I'll do a quick slideshow of it, and then this is a long chapter. I do want to do Newton's method because that's such a powerful, powerful tool. And we need to talk about differentials as well. So 3.9. Goodness gracious, this is going to take forever. But that'll be it. Good deal.
This is my second test. And can you fill out these
No, I
reports
can't.
for me and JB?
Okay. How do you spell failing?
What is, I think I know your,
He's
what
in my
course
biology class.
is his name Chris Tost?
Wait, I get them all in.
Huh?
Okay. First test, I'm still waiting to get those in. I just got another second. Still missing 2 people on the first test. But as soon as I get them, I'll take them. I'll have the grades on Blackboard at some point too, if they're not there already.
Thanks very much.
He is really cool. He did like this.
Goodness, they filled in the grade for them already, huh?
Really?
I was like, oh my goodness. It's really hard. I don't know.
Oh, yeah.
I just do the personal training.
Right.
He was on really well. He was really strong.
Uh-huh, yeah, he is.
I said, didn't y'all come here? He was like, no, I just come here for fun. I was like, oh, you crazy.
Right.
I have a question. I did my exam and I saw my score, and I don't want to see it yet, but I wanted to ask if I made a mistake on my quotient rule, because in class today, I have a habit of doing F prime G minus G prime F, which is the same thing as what y'all were doing. Y'all just saying it backwards. Because y'all say G prime F. I mean G times F prime minus F times G prime.
Well, you have to tell me which is the numerator and which is the denominator.
Well, this is the quotient rule.
Or are you talking about product rule?
I was talking about the quotient
Product rule is positive. Okay. Quotient rule, the way I remember it is using D and
You say low D, high D,
yes.
low, which is the same as the derivative of the top times the bottom minus.
Okay, Remember though, it's the bottom times the
Yeah.
derivative of the top times the bottom.
Times the bottom.
Yeah.
Here. And
Minus
the derivative of the bottom times the top.
Yeah. Okay.
So when I saw y'all in class, because y'all kept saying it, I had it written different. I think I went back and did it different on my test because I kept thinking y'all was doing the derivative of the bottom times the top minus. And if you look at my notes, that's what I did.
Okay.
I swapped it. I was like, I want this in my exam.
Okay, this is you. Oh, you're not in here. Oh, no. Okay. All right. So you have English over there and math here.
That's right. Thank you.
All right. And are those the only 2 courses you got?
No, I've got physics and online psychology. I gotta get those today.
Oh, okay.
Yeah, do we have to come to your office to see our test?
No, I've got them.
I bet it.
Okay.
Sounds like an